In a standard Apache Spark environment, the driver node acts as the central coordinator, distributing discrete computational tasks to a parallel fleet of worker nodes. These workers process segments of data locally through resilient distributed datasets. While this architecture efficiently handles narrow transformations, like filtering, it encounters a physical limit when a pipeline requires data points from different physical servers to be combined. This requirement triggers a shuffle, a process where Spark must relocate data across the network to group related elements together. During a shuffle, cross-node data transfer can easily exceed the capacity of the cluster's physical fabric. This network congestion often becomes the primary bottleneck, halting computation while nodes wait for incoming data packets. To prevent these bottlenecks, engineers must look past basic data mapping, utilizing specialized RDD typologies and manual control over distributed memory. Mastering these internal layers is necessary for building distributed pipelines that remain stable as the underlying dataset grows toward the petabyte range. The Cartesian transformation serves as a prime example of a completely naive operation that forces the cluster into a network bottleneck. This documentation highlights the core issue. To compute every possible combination of elements, Spark must pull data from different partitions that could be on entirely different servers. This results in a massive volume of data being sent over the network simultaneously. To mitigate this, Spark provides sophisticated action functions that can perform complex data processing within the local worker partitions before any data is sent across the network. The aggregate function is essential here. It uses a zero value to initialize, a seek op to process data locally, and a com op to merge results. Unlike reduce, aggregate allows a different return type, like aggregating integers into a pair representing sum and total count. By executing the sequence operations locally first, aggregate minimizes the amount of data sent to the driver, effectively reducing the network footprint of complex calculations. Beyond choosing better functions, we can also specialize the structural topology of the RDD to ensure related data remains physically close together on the same nodes. As seen here, pair RDDs organize data into key-value tuples, unlocking operations like reduce by key. By analyzing one key group at a time, Spark combines values locally before attempting cross-partition merging. You can build these pair RDDs from any standard dataset by applying a map or flat map transformation to extract a key from the raw data. This approach replicates the grouping capabilities of the Hadoop MapReduce framework. By grouping data by key in memory, Spark can perform computations on entire categories of data while minimizing cluster-wide shuffling. Enforcing this key value structure localizes the computational workload, ensuring that the cluster only moves the data that is absolutely necessary for the final result. For purely numerical workloads, Spark offers an even more specialized structure, the double RDD. For strictly numerical RDDs, Spark provides a specialized suite of actions to calculate sum, mean, standard deviation, and variance directly. Knowing the exact data type eliminates the need for engineers to write custom logic for basic statistics. Even for a simple array of doubles like 1.5, 3.5, and 2.0, these native functions can be called directly to return high-precision results from the distributed data. Double RDDs represent a highly optimized pipeline, allowing for the execution of standard statistical operations natively within the Spark core. While these data structures are efficient, Spark's default behavior of lazy evaluation can lead to a significant performance trap during iterative algorithms. This slide highlights the cost. Spark recomputes an RDD's content every time an action is invoked. In an iterative loop, this means the cluster wastefully recreates the same dataset from the original source files over and over again. To definitively stop this wasteful cycle, we must explicitly ask Spark to persist or cache the RDD across multiple operations. Under memory only, nodes store the RDD as deserialized objects in the JVM, allowing direct high-speed RAM access. If data exceeds memory, memory and disk stores the overflow on local disk. For high availability, the memory and disk 2 storage variants replicate every partition across two separate cluster nodes, providing vital fault tolerance against hardware failure. Explicit memory tiering allows Spark to maintain a state-aware environment, preventing repeated lineage recomputation. The final challenge in distributed state management is tracking global metrics, like account of data errors, without triggering an expensive network shuffle. Standard variables cannot do this. Because workers operate in isolation, any updates they make to a normal Python variable are never propagated back to the driver node. Spark solves this through accumulators, which are shared variables designed specifically for parallel addition. Workers use associative operations to push increments into a shared channel, securely aggregating a single global value. To maintain peak performance, workers are strictly limited to writing to the accumulator. Only the driver node has the authority to read the aggregated value. Accumulators provide a specialized write-only pipeline that allows for global state aggregation without the need for a cluster-wide data shuffle. We can now see the life cycle of an optimized distributed algorithm. Raw data is ingested and immediately transformed into a pair RDD to group related keys. This dataset is explicitly persisted to memory, ensuring iterative operations do not trigger full recomputations. Statistical subtasks are handled by double RDDs, using native actions to calculate variance and means directly from the cached partitions. Simultaneously, workers push row-level error counts up to the driver through an accumulator. The driver node retrieves the statistical results and the global error count at the same time, having bypassed multiple potential network bottlenecks. Advanced Spark programming is defined by the explicit management of distributed data structures and the tiering of cluster memory to minimize expensive network operations.